Good day, ladies and gentlemen, and you're very welcome to today's technical session of CNPS. We hold these technical sessions every fortnight, so I think this is the last one of the current month. Um, now, today we have the second part of a talk which was prepared by Dr. James Keene. Now, Jim has been very gallant, actually, in that he has elected to use his not inconsiderable skills in analyzing the feasibility of projects. He's done this professionally, I understand, for academics for a number of years. So we prevailed upon him to analyze two papers that had been drawn to our attention. The first one was a paper by Henri Cornier, basically on using a non-zero photon mass. And the second paper was by Peter Jackson on a measurement problem. Now, I'm glad to see that in our green room we actually have Peter here, and we have the speaker Jim. So we'll be talking to them, no doubt, in more detail later. But Jim went into quite an amount of analytical information 2 weeks ago, and we actually ran out of time. So we agreed that rather than sort of rush the proceedings with regard to analyzing Peter Jackson's paper, we should devote a full session to it, which would be something like up to an hour maximum, maybe 50 minutes or 60 minutes. So there will be plenty of time, maybe up to an hour, to engage in discussion. Now, I might just say I use the word gallant with regard to Jim's endeavors, because he's agreed to read some of these papers, or if I may say so, rather prolix and not always easy to understand by an outsider. They can even be a bit turgid. So he has agreed to use his skills, as I say, in analyzing this. Now, with regard to the first paper by Henri Cornier, we got some response back from Henri to say that he dissented from some of Jim's analysis. And in fact, he thought that Jim even had missed the central theses of his paper. Now, I had no problem with that. I don't think Jim did either. I had no problem. I said, we're here in the CNPS to debate subjects. We don't take umbrage at any personal slights if you disagree with me. In fact, we expect that. Otherwise, we're just really clones of each other. We analyze things. So what we're hoping to do is we're hoping to get Henri Cornier back in some weeks' time to talk fuller about his paper. And in fact, maybe expand a bit, because what Jim was analyzing, insofar as I could see anyway, was looking at the intersection between Cornier's ideas and Jim's own ideas. Now, he'll probably be doing the same with regard to Peter's paper. And Peter's here today, so it might be a bit more immediate that Peter will be able to come back during the discussion. And in fact, we're also negotiating with Peter. Some of my colleagues, I think it's Dennis Allen is doing at the moment, is negotiating with Peter that he would give his response. He would give a full paper in some weeks' time. So basically, that's it. Just to remind you about the functions, we have quite a number of people logged in through YouTube or Facebook, and they can put questions in the comment section. Now, any specific comments, we'll try to trawl through them, and we'll try to put them to the speaker later, and we can engage in some conversation, maybe to and fro conversation. But I'm alerted to the fact that a lot of the comments are just really, comments between persons saying, oh, that's good and that's rubbish and so on. So we won't be responding unless there's specific questions. I would ask that you leave your detailed questions until the end of the presentation in about an hour's time. Now, if there's something really very immediate that Jim seems to say a word that you didn't understand, or he said something that's completely over the top, you could put a note in, and he wouldn't mind being interrupted in extremis. But normally we'll keep the detailed questions until the end. Now, as I say, we have a virtual green room, and I expect maybe some more people will join later. So what we'll be doing is the people in the green room will have an opportunity of coming on and discussing at more leisure with the speaker, and perhaps also with Peter. some of these endeavors. So, and if people in the green room don't volunteer to come up, I'll probably request that they come up so we can have a more detailed conversation rather than have me spouting away and just after the speaker. So that's it. There is also a private chat section in the green room endeavor. So if you want to put anything privately, it just gets to the people in the green room, which obviously would include me. And I think if you get comments back, just label John Chappell, it's coming from me as the host. Whereas if you get a comment back from one of the speakers or one of the participants, it'll give his name. So that's it. So just to read before we introduce, so the original paper included actually Cornier's thesis and Jackson's thesis. So what we said is, or it was actually Jim Keene's words. Interesting work by Cornier and Jackson takes us into the microscopic world, including some mysteries in quantum mechanics, and illustrates some of the strengths and weaknesses of the theory of continuous space and time, which has dominated the thinking of physics up to the present. I might just say that Jim has his own ideas where he quantizes basically the units of length, time, and mass, but he'll probably be saying a bit more about that himself. So the how and the why certain theories fail is explored. Now, since he's dealt with Cornier's idea, we've entitled today's speech Jackson's Measurement Problem Analysis. So I'm going to hand over to Jim, and I'll take a few notes myself, because sometimes you can forget exactly what people said at the earlier part of the speech. So let me see. I bring Jim up. Hello, Jim. Good day. I'm going to get rid of myself, and I'm going to let you uninterrupted speak. And thank you once again for agreeing to be so flexible in giving these two sequential talks.
Well, thank you, Ian, for a very excellent introduction. I'm sharing my screen now. Can we put up the entire screen so that the writing is of a maximum size? Please get me off the screen.
Now,
can you see my screen now, ladies and gentlemen?
I've put it up, but we might have to maximize it as we have done before, Jim.
Well, my screen is full screen here.
Oh, okay.
It's in slideshow mode.
Okay, slideshow mode. I'm going to get rid of myself.
It is already in slideshow mode, the PowerPoint presentation. And I'll wait until you get that up. I can't see the screen that others are seeing now. I only see my own screen. So that
that worries me a little, because I think your own screen is probably in slideshow mode, but that doesn't mean that the screen that we have here, Jim, is, because we see your screen, I think, two papers and so on. And then we see just on the left a picture of you, say, and myself at the moment.
Well, get yourself and myself off.
Okay.
And I'll go to slideshow mode again. Now I have to skip past the first part of the talk on Cornier.
Sorry, Jim, but when I deleted you and me, we couldn't hear our audio. So unfortunately, Franklin is not here to help us. But so I'm just worried if I take myself down, you won't hear me speaking. If I take you down, we won't hear you speaking.
Well, then leave it as it is. Do you see review of papers as research proposals on the screen now as my first slide?
Yes.
Okie doke. Well, thank you again for an excellent introduction, and I'll get going. Okay, Ian?
That's perfect. There's some delay in my responding to you because I have to bring myself up to respond. But yes, that's fine. I'll leave it to you, Jim.
Bring yourself up if leave yourself up, because you're saying that my image is also appearing on the left of the screen, right?
Well, at the moment, I've just tried something else. I've tried putting it at the bottom. I'm going to try to get rid of it altogether and see. Can you still hear? Can you hear me?
Yes.
Okay.
And
So what I've
if
done
you
is
can get rid of my image too, then my
Yeah.
screen in the
Yeah.
slideshow mode would be full screen for our CNPNS folks.
I've succeeded in doing that. It meant that I had to choose cinema layout, which I've done, which means that our images are gone and we have full screen. So it seems to be perfect. And yet we can hear each other.
Okay, fantastic, Ian. Please chime in at any point, Ian. Should I then proceed with my little presentation for the day?
So please proceed. It's now sort of 10 past the hour. So
Okay.
you've got plenty of time. Thanks,
Okay,
Jim.
here we go. First, thanks for the wonderful introduction, and I welcome with warm greetings Mr. Peter Jackson as well for us today, and I look forward to hearing from him. I'm going to use my experience as reviewer of papers for peer-reviewed journals of NIH and NSF grant proposals. And I'm going to apply guidance to site visit teams, which I chaired, namely that each team member, as an expert in both theory and research methods, should focus on helping the investigator be successful in their research plans. If a weakness is noted, explain how to fix the problem, because we're trying to help the investigator. For example, if let's say the literature review misses some article, it could be the fix for the problem is simply to mention that article or that issue, because it could be that no one has an answer for that issue. But the fact that it's mentioned and recognized by the principal investigator indicates that the investigator is aware of what the problems are or potential problems are with a particular line of research. Thus, we're going to view a paper as a journal submission or research proposal and enumerate strengths and weaknesses. And in so doing, as promised in the abstract for this presentation, we'll also be looking at the general weaknesses in the theory that space and time are continuous. So here is a little image, The Measurement Problem and Ontological Solution by Peter A. Jackson and John S. Minkowski. There's actually two authors here, although I usually mention the name of Jackson in my comments. You'll note that this is a post-peer review copy. Now, one advantage of these CNPS sessions, in my personal point of view, is that a number of the people that are regular participants, and we welcome newcomers as well, think outside the box with regard to conventional physics beliefs and perspectives. And so my peer review may be somewhat different than the peer review that this paper previously has received, because I and others in this group tend to look outside the box of what we might call mainstream physics. Now, a very good sentence is the first one of the abstract. A physical mechanical sequence, think about that, sequence is proposed representing measurement interactions hidden within quantum mechanics' proverbial black box. I consider this a very strong, excellent first statement of research objective for this paper. Now, microscopic physics is hidden in plain sight. And in this case, it's in the red boxes in this illustration. Let's walk through some of this, because Dr. Jackson has focused on a very important issue in quantum physics. First, let's look at Newton's first law. We tend to draw an arrow, and then we're going to get a little bit fancy and call it a vector of something moving from position r equals 0 to r equals 1 in arbitrary units. But what is the motion mechanism? How do things move? In other words, we have an arrow, but how does whatever the thing is here at r0 actually get to r equals 1 position? Now, in physics, we tend to overlook the basic questions of what the science of physics is supposed to be about, which is how things work. I might mention in biology and in chemistry, this would be unacceptable. If we observe a phenomena such as something changes position, a displacement from one point to another point, we want to know how it got from this point to that point. We want to know the detailed mechanisms. In a caterpillar crawling from one point to another, we want to analyze exactly how the segments of that caterpillar move. How do they move? What are the contractile proteins involved? In other words, hidden in plain sight in this typical illustration using a vector or an arrow in Newtonian mechanics is what the real physics is, but we never get to the real physics. How about particle interactions? Here's a Feynman diagram where the vertex point where the arrows meet is where the real physics is. The vertices here and here hides the mechanism. The vertex hides the mechanism. Okay, now let's look at lattice chromodynamics, which has to do with analysis of the internal structure of the proton and nucleons in general. Here I've shown in 2 dimensions what would normally we would have in three dimensions, a proton, which I just depicted as a circle in a lattice. In the primary length constant that I spoke of 2 weeks ago would be shown here in a particular lattice, although that's not the one necessarily that the lattice chromodynamics people use. The fact that they break down the various fields which are thought to be involved in proton structure and the internal mechanics of how protons move and are structured is hidden in the lattice chromodynamics, but nobody actually says maybe there is a real lattice. So it's hidden in the lattice chromodynamics, the actual microscopic physics. Lastly, we have the base units of measurement in physics: length, time, and measurement. So hidden in plain sight are the units of the primary constants in what I described 2 weeks ago as binary mechanical thinking. So this is all to go that to the point that Jackson's objective in the first sentence of his abstract is outstanding, is very welcome. Now here are Jackson's particles as balls or spheres, or are they balls or spheres? And this is one of his illustrations, and he talks about measurement being considered as a momentum exchange at some point on the sphere surface between, I guess, 2 objects, the signal coming into a sensor and the sensor click or indication that an event has taken place at that sensor. So here he's considering particles as spheres or balls. I mentioned the term balls first and put spheres in parentheses here because it reminds me, at least, of back to Newtonian mechanics of billiard balls, which can have spin and so forth and interact on a table. And so it'd be interesting to find out how this goes beyond that. And Mr. Jackson and Mikowski provide a rather detailed analysis of how they think that happens. No, notice that we have up and down spins, which can be determined or sensed depending upon which surface of the ball or sphere is interacting with a sensor, which I guess would be another sphere in the sensor. Now, one big mistake, in my opinion anyway, is that particles in the classic Stern-Gerlach experiment were thought to have up and down spins. In other words, two quantum categories of particles. Now, a big problem with that concept is that, by the way, in the Stern-Gerlach experiments, I recall that the ions used originally were silver ions. In other words, a rather complex structure, as opposed to, say, a single proton, a hydrogen ion, in other words. At any rate, when you split in a magnetic field a beam of these particles into so-called up and down groups, these are really different sets of particles, are thought to be different sets of particles. Yet, if, in other words, one of the split beams is thought to be the up particles and the other one is thought to be the down particles. Now, if you take one of those two beams and split them again, and split that beam again, in other words, all the so-called up particles and or all the so-called down particles, and you split that beam again, you're going to get two more beams of up and down particles. What this indicates, and this is experimental data, this is not theory I'm talking about here. What this indicates to me anyway is that there is no such thing as an up or down spin particle. It is more the how that particle interacts with the magnetic field and what the details of that interaction are. Now, to the credit of Jackson and his co-author, he seems to agree with that point of view. And I mentioned the Stern-Gerlach experiments because in his paper, this subject does come up. And here he depicts the so-called up and down properties as merely, well, perhaps I shouldn't say merely, or as two parts of the sphere, which may interact, I guess, with another sphere in the detector in the measurement situation he seeks to describe. And it only depends upon which portion of the spheres actually touch or encounter each other as to whether or not we're going to call it up or down. In other words, if this portion of the sphere interacts with the sensor sphere, I guess, I'm not sure he actually says that the sensors also are spheres, but at any rate, what we're going to have is an up type interaction, whereas on this side, the spin would be seen, the spin of the spheres, which Jackson hypothesized can occur in actually 3 dimensions, would be detected as down. Okay, more questions, or some questions, perhaps I haven't asked any yet, on this interesting paper. Is measurement as momentum exchange another black box? Okay, I went through the 4 black boxes, and there are more than 4 in a previous slide for a reason, because I'll ask you, the listeners, to start to think about, is depicting a particle as a sphere another black box? Or do we want to really know what is happening more precisely in a physical sense at those points of interaction between the spheric particles and the sensors in measurement? Second, is consideration of particles as spheres consistent with other observations? This is something that I think merits some thought. Examples. Scattering data suggests that ions, atomic nuclei, appear to exhibit non-spherical shapes, starting with single protons. In other words, in mainstream physics, you're going to see those quantum chromodynamic and presentations of the proton all showing a sphere, yet their own people at major mainstream institutions, Harvard, various institutions, Cambridge in the UK, at CERN, etc., their scattering experiments seem to indicate a non-spherical shape. How do they detect this? Well, if you have spherical billiard balls, you can predict the trajectory of deflection or displacement when the momentum of one ball hits another ball at a certain angle, and it forms a very uniform curve. If that curve is not as expected from simple Newtonian mechanics of billiard balls interacting, and by the way, billiard balls can spin also, as well as baseballs in American baseball and so forth. The data actually shows a spectrum of trajectories which contradicts the spherical shape hypothesis, and yet people continue to assume that the proton and other particles used in experiments are spheres. So here we have a real contradiction within mainstream physics of what's going on. They ignore existing data that their own folks produce. Point two about is consideration of particles as spheres consistent with observations. I mentioned the Stern-Gerlach experiments discussed may use a variety of particles, such as silver ions, which probably do not have spherical shapes. Finally, there are plenty of questions, but I'm just listing a few that came to mind. Does in other words, Jackson and Minkowski's spinning spheres model yield new insights or ideas for future experiments to resolve basic issues? When we're evaluating a paper submitted for publication or a research proposal submitted for funding, the author gets a chance at the end to point out, how their work can lead to future experiments and how their work might develop to resolve basic issues in science. And so does the spinning spheres model yield new insights or ideas for future experiments is a question on the table, if you will. Okay, Jackson and Minkowski analysis. Let's look at some of the strengths. I've already referred to some. A physical mechanical sequence is proposed representing measurement interactions hidden within quantum mechanics' proverbial black box. Excellent. Quantum mechanical theory gives no measurement mechanism or physical explanation of how wave functions, collapse, or change to give post-measurement states. And this is a direct quote from Jackson. A good statement. Here we suggest a new, simpler physical cause for measurement uncertainty. Again, another quote, which I've truncated, ... And he has, in general, a good review of weaknesses of quantum mechanical theory. This is very welcome here at CNPS. And again, I welcome Jackson to our proceedings today. He cites, cite data violating Bell's inequalities without needing non-locality or implied action at a distance, removal of any need for long-range supraluminal communication. Another strength which we might explicitly list is recognition that a single particle may be classified as upspin or downspin depending on spatial relation to other events. This I already commented on in a little bit of detail a few moments ago. How about some weaknesses? Are there any? Well, in anybody's work, you could always point out some weaknesses which may really have to do with questions that people would have. At any rate, I have listed a few points here. Considering here's a quote from Jackson again, Jackson et al. Considering as spherical orbital angular momentum, OAM, quite a mouthful there, rotation, let me say that again. Considered as spherical rotation, we can leave out this part here and just keep it in mind. We invoke the unique quality of spheres to rotate concurrently on three axes. Rotating on Y or Z axes concurrent with X axis spin can return surface points to starting positions with non-integer X-axis rotations from half to infinity. This has to do with, in quantum mechanics, people are talking about fermion particles have 1/2 spin, and so-called boson-type particles have one spin, unit one spin. And this, of course, is measured in terms of the reduced Heisenberg, Planck's constant, the reduced Planck's constant, I should say. This sphere model and use of vector addition, remember we looked at vectors and vector addition in both Newtonian mechanics and Feynman diagrams to some extent, you might say, in our little tour of black boxes at the beginning of this presentation. This sphere model and use of vector addition, which is a term that Jackson uses, to represent interactions, firmly place their analysis under the aegis of the theory that space and time are continuous. Again, I mentioned right at the outset that this paper that I read is a post-peer-reviewed paper, which means that the reviewers almost certainly were operating under the aegis of the theory that space and time are continuous. In other words, whether or not that is true would not even be an issue. Although I might add that more and more physicists, such as the loop gravity group, are starting to question this and starting to talk about discrete units of space as well as of time. And so that the trend in mainstream physics, there is a breakaway group, as it were, that are questioning this theory that space and time are continuous. Size of hypothesized spheres are not considered. It could be somewhere in the paper and I just missed it. But at any rate, this is an important point. When we're talking about physics, which is how things work, we want to know how big things are, what their size is. We're not in literature or poetry where we can make metaphors, even using fancy mathematic metaphors. We're actually wanting to know what the actual physical events are, just as the biologists and chemists do when they want to know how two different molecules interact to form a different compound, or how, for the biologist, a caterpillar moves from point A to point B. They want to know in terms of not poetry, literature, metaphors. They want to know exactly what's going on physically. The use of complex vector additions may add another black box. Now, the term complex, there's such a thing as real vectors and complex vectors, which means that each basis component of the vector is in fact a complex value in terms of the complex numbers. So I'm not sure exactly what is meant here in this paper when the term complex vector additions. It could just mean a number of vector additions, which, when taken together, gives you a rather complex picture, or that complex numbers are actually used. So perhaps Jackson can clarify that for us. No mention that the bit function representing position and momentum simultaneously and is therefore superior to the wave function. Use of the dipole electron model. This is a direct quote, and frankly, I didn't understand it, because this contradicts widely accepted measurement, excuse me, widely accepted measurement that the electron electric dipole moment is zero, both from a well-known group at Harvard, as well as another rather well-known group in the UK, have come out with measurements of the dipole moment of the electron, and found that it is not significantly different from zero. That, you know, in other words, confirming the hypothesis that it is zero. Another thing that you're going to see here, but perhaps not in mainstream reviews, is that the paper misses the benefit of full quantization as a route to fix quantum mechanics problems. Now, what are some of these problems? The mother of all theories here is our mother sow, the theory that space and time are continuous, and any problems or limitations in the piglets, which go all the way back to antiquity, actually, but I've listed here our classical physics piglet, the special and general relativity piglet, the quantum mechanics piggy, and the standard model piggy. All of these depend upon the theory or assume that space and time are continuous. Now, are there adverse reactions or side effects of conventional physics classes? The contradictions are ignored observations and experiments. I've already mentioned several of these. One could go on all day and spend a whole hour just talking about contradictions. And many of our regular participants here in the CNPS sessions have done this and made a number of presentations about contradictions among observations. Dualities, wave versus particle. Any duality that you want to list in conventional physics is really an explicit admission of inability to explain results. Here you have one set of results that indicate or suggest to us that a wave is involved, and another set of results that a particle is involved. Well, if we were able to fully explain these results, there would be no duality. So the dualities indicate inability to explain results. And paradoxes, the twin paradox, again, all of these paradoxes that one likes to talk about indicate flaws in theory. Now, one thing that we see a lot in physics literature is people pointing out a new paradox, as if they're actually contributing to the advance of knowledge in physics. Well, there wouldn't be a paradox if we were actually getting close to the goalpost because a correct theory would have no paradoxes. So if there's a paradox, it indicates that your assumptions are flawed. Uncertainties, position versus momentum, again, that indicates unknowns. Magic, unknown how things change position. Magic is an illusion. So our one definition of magic points out the word illusion. So that what we have is a lot of people believing in magic. They don't even ask how the illusion works. You'll hear long expositions on Newtonian mechanics and so forth without even a whisper of how object A gets to object from point A to point B. Miracles are really very popular in conventional physics. It's impossible things. Infinite number of infinitely small supercomputers are required at every point in space in field theories. You're going to have a particular potential at a particular point in space, a gravitational potential, electric potential, magnetic potential, whatever it might be, which is the summation of a large number or even infinite number of things. And of course, if we were doing physics, which of course we're not doing physics, but if we were, we'd say, well, at this little point in space, where we have this field based upon distant objects, there must be, and since there's an infinite number of points, there must be an infinite number of infinitely small supercomputers required at every point in space. So that belief in miracles is really typical in mainstream physics. Again, suspension of disbelief, as in a movie. To get you sucked into the theme of a movie, you may have to suspend disbelief, which means basically many questions are not allowed in current physics classes and conventional physics thinking among those who have graduated from those classes and are out publishing papers and so forth. Equation collapse. The math works only when we're not watching. This is a very egocentric view of the world. It reminds me of the time when people thought the sun revolved and stars revolved around the earth. Everything revolves around us. It's in terms of uncertainties and the Heisenberg uncertainty idea, it's the idea that the universe is dumb. It's not us that don't understand it. It's that the universe is dumb. That's the dumb universe model of Heisenberg uncertainties, which actually, if I may, just as an aside, point out, this has to do more with measurement error or measurement uncertainty, and not that the universe is actually dumb, which is the basic theory that most physicists accept. And then the Planck limits, another magical mystery tour, and I'll give credit to the Beatles, the musical group from the UK. The Planck limits, boy, that's another side effect and adverse reaction. Here's our magical mystery tour, the Planck length, time, and mass. Here we have a formula for each for the length, the time, and the mass. And I don't know how this guy got in here. That's a mistake. Ignore that. And here we have our international system of SI units, the meter, second, and kilogram, for quantities, which everyone seems to agree on. You look at the constants in the appendix of any physics textbook, just about, you're going to find that everything is expressed in terms of length, time, and mass. Now, the magical mystery tour down here to the lower right is the Planck's constant. And by the way, here are the primary constants in binary mechanics, which I threw in. And here's the ratio between the two. These are off by a great deal. Now, let's take a look at length. The conventional physics people will often say, you'll hear it said, that below the Planck length, this incredibly small distance in meters, 20 orders of magnitude less than the primary constant in binary mechanics, that less than this Planck length, the laws of physics may not apply. Well, they're really dreaming, because guess what? These constants for gravity, light speed, and the reduced Planck's constant, h, are all secondary constants themselves. So when you take things that we don't understand, in other words, up until recently, no one has explained why light speed has the measured speed that it does, and not something like 100x greater or 100x or 10x smaller. The same with Planck's constant and the so-called gravitational constant. So that here we have unexplained observations used to make more unexplained stuff, the Planck length, time, and mass. So that's our magical mystery tour. And for those who are wetting their feet trying to get into full quantization, or even partial quantization just of length or time, or maybe two of the three main dimensions here, they are way off. They're orders of magnitude off. Now, if the laws of physics are thought maybe that would be questionable, or perhaps not work below, for distances below the so-called Planck magical mystery tour length, here, what about the magical mystery tour mass? The proton, the electron, is some 22 orders of magnitude smaller or less than the Planck mass. Does that mean that the electron, that the laws of physics are broken? So which is it? Above the Planck constant or below the Planck constant? It's entirely arbitrary, entirely a story that is more appropriate for theology schools and literature and fantasy poetry than for the science of physics. Okay, the adverse reactions to classical assumptions can be fatal, as I've said. The injections worked, Watson. Now the student will not question the theory that space and time are continuous. And here are all the injections which the student received from the classical physics classes. It's a wonder that someone like Jackson and his colleague Minkowski could survive all of these injections and come up with some fine, original, and critical thinking. Conclusions. The abstract for this talk featured flaws in the theory that space and time are continuous. Okay, we tried to cover some of those flaws. However, as reviewer of these two papers, the goal was to present strengths and weaknesses based upon generally accepted criteria, omitting reviewer bias. In other words, any bias you think that I might have because of my own work in binary mechanics with full quantization. And binary mechanics is simply an alias for what we call full, complete quantum mechanics. You can review any reviewer bias I may have on that score and just look at the generally accepted criteria if you so desire. Authors of both papers, I didn't get to present these conclusions 2 weeks ago, so here I'm saying of both papers, Cornier and the one today on Jackson's measurement problem, display competence in literature related to their chosen research questions. No doubt about it. This reviewer suggests that the authors are able to address identified weaknesses. And why would they want to do that? They would thereby receive wider approval of their work. In other words, we have a happy ending. Now, Dad, why can't physicists explain how things work? And Dad replies, well, we believe that space and time are continuous. Now, is this just a funny little cartoon-like meme that I'm presenting here? I'd like to go one step further, if you'll allow me. Let me check the time. And the time is, okay, we're at the 50-minute mark of the first hour. So I do have a few minutes, perhaps. I'd like to expand this and say that with the side effects, there were more than half a dozen side effects of the theory that space and time are continuous, what I called adverse reactions. I'd like to take that a little step further and say that nobody will solve the basic unexplained questions in physics, including quantum mechanics, black boxes that Jackson and Minkowski so rightly focused on, and gravity and how that might be integrated with quantum theory, that no one in mainstream physics using are confined to or captured inside the box of that theory that space and time are continuous will be able ever to solve these problems. Okay, it's almost like a mathematical axiom that I'm presenting here. As long as you stay within that box of continuous space and time, excuse me, as long as you stay confined in that box of continuous space and time, you'll never be able to address basic questions of how things work, which is to get physics back to the level that chemistry and biology already are, in terms of looking for physical mechanisms of what's going on in this universe and reverse engineering the universe. Okay, so a theoretical physicist growing up. Let's look at this. Son, one day you'll be a man. But Dad, I'm 32 years old. Well, son, you still fantasize that space and time are continuous. And finally, I'll stop here. I'll leave this on the screen for a moment. And I'll turn it back to Ian and ask whether I should stop screen sharing or what, so I can see everybody. But this, I guess, let's see, is that the end? Yeah, that's the end.
Right. Thank you very much, Jim. I'll let me see.
Let's see. How do I? Okay.
Can I change the format? So at least
stop
we have
screen. Okay, I stopped the screen.
Right. Well, thank you very much indeed. I'm even more in awe than I was at the beginning at your capacity to get to the center of these papers. And I mean, evidently there is quite a commonality between you and Peter's thesis in regard to the discreteness of space, whereas I think there might have been some difference between you and Cornier, but this will come out in our further discussions.
Well, if I just may chime in quickly, it's people have been viewing the two papers by Jackson on the one hand and Cornier on the other hand as being two different subjects: the massive photon and the measurement problem or black box in quantum mechanics. I viewed them both as addressing the same basic issues of whether or not it's even possible to address fundamental questions in physics within the framework of continuous space-time theory. Sorry for interrupting you. Keep going, Ian.
No, thank you very much. That did clarify it. And I just wanted to make one or two brief points just before inviting people from the green room. Indeed, in the first instance, Peter himself, because we have the author of the paper. But by the way, I take it it's the paper which was published in Foundations in Physics in August of 2021, and it can be downloaded free of charge. You can just Google Peter Jackson measurement problem, and you'll get it. Yeah, so I was interested in maybe the reality or otherwise of the up and down spin that you concentrated on. We
Well,
even
this was one of Jackson's strengths, I believe.
Yes, quite so. And the non-sphericity, perhaps, of these elementary particles. And I was just thinking that the sort of sphericity is not really stable per se. Like in the orbits of the planets, if you get a spherical or a circular orbit, well, it's not stable. Any small perturbation will not lead to a negative feedback. Whereas if you have an elliptical orbit, it does, and it gets back on course. So that might be another way of looking at
I'd
perhaps non-sphericity.
like to see someone present that in more detail.
Yes. One will have to give a lot more thought to these points, actually. But they have been raised by your analysis, Jim. I might have a point on the contention of Jackson. Maybe he may answer this later. That he's not resorting to non-locality and maybe superluminal speeds. So I just might ask him if those things are conceivably possible in his thing. And of course, you had one question yourself. Sorry if I'm acting a bit as a schoolmaster here, just making sure we pick up things. You said we may have to address what Peter meant by complex vector addition, because you were getting...
What was your first point? I think we should pause rather than just listing a whole bunch of points. What was the first?
I just
you
really
made 2 points in your last segment.
I've maybe only one question there, but the others were just, I just noted that it appeared that the spin, the up and down, might be really artificial concepts.
Yes, well, for quite a while, the quantum guys were talking about the beam splitter is actually creating beams of 2 types of particles, but then some folks came along and said, well, let's split one of the so-called pure up beams, and we find, lo and behold, we get up and down beams all over again, which suggests that actually it's some more complex interaction between the I hate to use the term field, but okay, let's do it, between the magnetic field used to split the beams and the particular trajectory or orientation of the particles at the time the beams are split, if you will. Okay. And Jackson recognizes this problem. And with regard to the superluminal, I just remembered the first point that I asked you to remember in your comment. Yeah. There are a number of papers which question or show that entirely classical physics notions, like of Newtonian mechanics and so forth, can account for what appears to be superluminal communication or superluminal communication. So Jackson, as far as I know, is not the first one to point this out. And I'd have to go into his references and so forth. Perhaps he is citing these previous papers. I suppose he might be, or I'm sure he's aware of them. So the idea that these experiments violate or demonstrate communication faster than the speed of light is one that's been debunked, as Jackson has pointed out.
Okay, well, as I intimated earlier, you've taken on the very brave task and a very valuable task of giving us your own take on these points which are raised. And we're very privileged actually to have Peter here today with us. I saw one of the emails recently to Dennis Allen. I think that he would try to participate today, but he wasn't sure if he'd be able to. So I'm delighted he is. And I'm going to bring him up now, if he'd agree, and we'll have a brief conversation. And, I say warts and all, I mean, in a more formal setting, we might have a proposer of the vote of thanks to the speaker, and I think that would be well deserved. We don't normally have a formal thing, but if Peter would like to, sort of substantiate anything you said, or contradict anything you've said, or even be a bit nasty and say that you completely misunderstood his paper. We're all grown-up adults, and we're happy to talk about this. All we want is truth.
Sure.
We don't want politeness or anything like that. So I'm going to bring Peter up himself, and you might like to say a couple of words about yourself, Peter, and then maybe address yourself in response to Jim's presentation of your ideas today. I may have to unmute you. Hold on a second. We can't hear you. I think you're muted. Yes, you're unmuted now.
Okay, you can hear me okay now?
Can hear you. Yes.
Great. Okay. Yeah. First off, thanks to Jim for quite a brilliant analysis. That was absolutely excellent, Jim, with some good background there. I agree with just about every point Jim said, so I've got nothing to take issue with, really. There were a few dozen questions raised, really, all of which can be answered, and some of which are answered in the paper. Jim did sort of miss a few bits, a few of the subtleties in there. But I'm not surprised. It was a very difficult paper to read. It took the Springer Nature peer reviewers some months to actually completely get their heads around the theory and the model and to follow it through, because it is very complicated and it's multifaceted. And you've got to look through and deal with consequences of each element each time. To end up with a result which comes down to effectively reproducing the experimental results causally, which is a bit of a shock, of course, and conventional physics beliefs aren't going to accept that straight away, maybe in a few decades. But if I can just explain to you then how it does work in terms of Jim's comments. How I came to this really was after considerable research in other areas of physics and evolving a discrete field model of space, and I won't say space and time, but of space itself as consistent actually with an ignored paper of Einstein, his final paper of 1952, where he described space as infinitely many spaces in relative motion within larger spaces. So bounded, finite regions of space. So a fluid, any normal fluid or gas, which has flows and boundary conditions, which are shear planes, where vortices arise. And that model proved particularly successful. There have been a number of papers on it, and it was very well received in the FQXISA competitions. But I decided that really the final proof of that would be if that model could solve the problems of QM. So I tried to avoid actually getting too deep into QM previously. So I decided to delve into it and try and use the new approach to see if we could find a better analysis of QM. And found that after it took about 2.5 years, but that did seem to come together, and that included a couple of FQXI essays, which were very well received and peer scored. And addressed wave particle duality. To simplify that one, if you we all know that all light has helicity, a certain degree of helicity, and all helicity has a certain degree of ellipticity, as all orbits are elliptical, as you correctly said. So if we look at a helix, then can you tell me if that's, when it's observed, is it a wave or a particle? If it's observed on its axis, it has full rotations, so it's particulate. If it's observed from any other angle, it's a wave, and it's an ellipticized helix. So it's a set of motions. So we then come to continuous space. And I think continuity is something that we have to consider in terms of scales and gauges. If we consider a cyclone as an entity, then we consider the medium making up that entity as continuous, as Lagrangian. But of course, we know it's not. It's air molecules and the rest of it. So and then we look at molecular structure, and the further we go down, we consider the next stage down as continuous. But then when we actually get to look at it more closely, we realize, well, actually, it's not. It's a fluid. So if we work on the assumption that space is the condensate, and this answers a very big question, that the condensate from which matter condenses is actually a medium, a fluid medium, made up of smaller particles, which can be granular, is a popular term, down to not only down to the Planck length, which I agree isn't a finite limit, but in fact, Stephen Wolfram, developed a very, very elegant theory and hypothesis that the basic fundamental length is down to 10 to the minus 93. Very many orders further down below the Planck length. And the Planck length itself is very many orders down from the electron, classic electron size. So here we're dealing with, and I'm not really defining size for the medium condensate, but to say that, look, it can be anywhere, but the smallest form of condensed matter is the fermion, is the electron, positron, or quark. But there is a scale down below that, because we've got to ask, what are those made of? And then we answer the question, what does happen between Jim's two ends of his first box, which goes back to Faraday. Action at a distance, which has always been a buried hidden answer we avoid answering. How does electromagnetism transfer from one point to another? And my answer is that yes, it is. It's motions in the fluid medium, but that fluid medium can be quantized. It can't be actually quantized because a quanta is matter, is condensed matter. So it's actually subquantum. But this is some really background which allows other answers to be arrived at and the main problems to be solved. So if I can go back then to Jim's main questions, first of all, the sphere. When Jim's diagram was up there, we talked a lot, or Jim talked a lot about the plus minus, which is up down, but not a lot about the other state which I describe. I say that actually it's quite uniquely, apart from very specialist areas like spin statistics theorems, there are two sets of momentum on a rotating sphere. Now, a sphere is a simplification, okay, and I've simplified it for ease of handling. It then extends to almost anything. So, in fact, we fully explain wave-particle duality, including the helical view. So, if we can actually, I think we should be able to just see the sphere behind my shoulder rotating. it's got an equatorial linear momentum, plus it's got a polar curl. We go back to Maxwell. He had two momenta. We didn't know what they were, so we completely forgot them. I haven't seen them mentioned in physics for decades. So we've got the North Pole of Earth rotates in an anti-clockwise direction. If we arrive at Earth with the North Pole facing us, we find it spinning anti-clockwise because the sun rises in the east. If we happen to arrive over Australia, we find it spinning clockwise. The opposite is plus rotation. It is a rotational dipole. Everything that rotates with a plus rotation also has an equal minus rotation, depending on which way you look at it. What a famous phrase that ought to be. So we can either flip the, let's do it with the globe. We can either flip the globe so that instead of spinning one way, we find it's actually spinning the other way. Okay, or we can change our attitude. We can come at it, what's relatively speaking, upside down, because there's no up in space. Or we just happen to come at it from a different direction. Now we can then move on to the business, what I'm talking about as complex vector analysis.
Yes, I was going to bring that in.
Can you see that? So complex vector analysis, we say, okay, when we have an interaction at any particular point on the sphere, now this interaction can be with another particle. So I've said, look, let's deal with electrons for a moment. We were saying there's two lots of electrons. A lot of experiments are with electrons, whatever they are. So we model them as spheres, which can have ellipticity if we wish. But it can also be with a plane wave. So we can have a very far distant signal arriving at the sphere as effectively a plane wave. It will still interact at some tangent point on the sphere, some angle. Okay, now, so whether it's a sphere, electron, or a wave, exactly the same thing happens. We get an interaction between the two. Now, 2 points here. Firstly, these two qualities, the rotation, plus or minus, top and bottom, and the linear, left or right, depending on which way we happen to arrive at it as well, or which way up it is. And all bodies out there in space are equal. They both have both in equal measure. There is a distribution of momentum between the two. Now, those familiar with QM will recognize this. The change between, let's look at it in terms of Earth's rotational speed to start with, because it's easy to imagine. The speed of rotation of Earth is around about 1,000 miles an hour on the equator, say. It actually is, nearly. When you get to near the pole, it's actually a hell of a lot less than that. And you get to the pole and it's zero. You haven't got any linear speed at all if you're standing on the pole. So that change is non-linear by the cosine of the angle of latitude. Now you need to remember this, because when we look at the other quality, which is the polar rotation, that also goes to zero over 90 degrees by the same rate, the cosine of the angle of latitude. So over 90 degrees, it goes from 1 to 0. And those two qualities go from 1 to 0 inversely with the angle of latitude over the quadrant. Needs a bit of thought.
The sine of the co-latitude. Yeah.
Sorry?
Sorry, it's a sign of the cold attitude. But I just sorry to come in there, but I just hope I'm being a bit direct now.
Yep.
I hope you are going to agree maybe next month to give us a fuller talk, Peter, and that I'd like you to save a lot of these ideas, maybe with some slides if you have them, to give us that talk.
I will hopefully do that. I can actually just go through the sequence now, having set out the basis for it, which should be then understandable, and you should be able to obtain from that how the weirdest thing about QM are naturally reproduced. You got time to do that?
We have time briefly to do that. There are a couple of people in the green room. I'd like to get their response as well. But basically, I'll give you the floor to do that and be grateful. And in fact, I just comment that I'm actually tickled pink in a way, that your first response was equivalent to my own. It was a congratulation of Jim for having got to the core of your ideas, and you were quite complimentary on him. So I was quite happy to hear that. But I'll let you give the brief order of maybe your proposed presentation, Peter. Thank you.
Okie dokie. Well, let's then make some assumptions about what happens in the Stern-Gerlach experiment, or similar experiment to the original Stern-Gerlach. Let's assume that a beam splitter produces two identical particles, and they're identical to the extent that north and south both face the same way. So if one goes that way and the other one goes that way, one's being led by its north polar axis, the other one's being led by its south polar axis. So they're identical particles, but they also have absolutely random polar axis angles. So they're both the same, so they're anti-parallel, but they're absolutely random how they turn out. So it may be north going that way, it may be north going that way, which means the south is going the other way. Now that turns out to be exactly the effect when I go through the rest of it, which turns out to be entanglement. It's anti-parallel polar axes. So it can be any axis, any pole, but they remain parallel with each other. They come out of the splitter identical and they remain parallel axes. And they then arrive at the polarizer electrons, okay, which we really do know are electrons theoretically. So we then have a situation where if we've got a plus arriving at Bob's polarizer, we should have a minus arriving at Alice's polarizer. But that's if they've got the same polarizer angle. So famously in QM, Bob and Alice can change and reverse their polarizers at will. So completely change plus to minus. And what we get is a plus minus, depending on how they set them out, is changed to a plus plus or a minus minus. So in theory, the way Niels Bohr imagined it, there was only one momentum in OAM, but we now know there are two inversely proportional over 90 degrees. So when these hit the polarizer particles, okay, we then have a complex, that's what I call the complex vector analysis, is the fact that we can, let's have a more manageable globe here, is that we can rotate this. So I've got a video, it's on YouTube, which shows how we get X, Y, and Z momentum rotations and momenta are happening at the same time. We can actually do that. A sphere is uniquely what's a spheroid, uniquely can rotate in more than one direction at the same time without having momentum issues. So we then have to have, when that interaction occurs, and I say size doesn't matter. This could be a plane. When it occurs at some tangent points, we're actually talking about absorption and re-emission. We know electrons have the highest absorption coefficient, or highest coupling coefficient, it's called, of any particle, which means they absorb and re-emit EM fluctuations. So we're not talking about billiard balls. What comes in is then combined by three-way XYZ vector analysis, which is actually, if anyone's familiar with spin statistics theorems, that's how they try and make them work. They haven't quite got the answers to any of them yet. There are a few around and none of them quite work. But that's how they should work, and that's the basis. There's an X, Y, and Z axis, because Bob and Alice can have their polarizer at any particular angle and attitude. And when something arrives, it's the relationship between the two. Now, everybody, Niels Bohr, in fact, it was first von Neumann who said the meter is part of the system producing the result. Niels Bohr and Werner Heisenberg said that, in fact, the interaction with the meter, which in this case is the polarizer, changes the state of the incoming signal. So the outgoing signal is then a combination of the two different lots of spins. So the wave function is modulated by the polarizer. The polarizer does actually polarize. It repolarizes the signal coming in. But the key thing here is that the entanglements, the weird thing about QM, that Bob can change Alice's finding at infinite distance, is no longer required, because Bob can reverse his own finding by reversing his setting dial. If he reverses his setting dial, he goes from plus to minus output, and then we receive exactly the same statistics that QM assumed only came from one OAM, one set of spin.
Peter, I'm sorry, but would it be possible for you, maybe in the coming weeks, to give us just a one-line title and maybe a three-line max description of what you might propose to present to us, maybe in March? That would be very, very useful, because we can put that into the program.
Yeah, I could. I'll probably do that.
Yeah, I know you have Denny. You could either send it to Denny Allen or you could send it to me. You have his email, so if you send it to Dennis, that should suffice. Thank you very much. Because what I'm going to do, with your permission, and also with Jim's, actually, I hope you'll forgive me for this. I'm not going to ask Jim to come back to respond to your points immediately, but rather I might take the opportunity of getting some comments from one or two other people in the green room, and then I'll ask Jim to come back and summarize the lot, including a response to your response to his paper. So if that is agreeable, I'll do that now. Eric, if you have some brief points, we are running a bit out of time, but if you have some brief response, I just want to unmute you first. Yes, you're unmuted. I'll bring you up. It's Eric there, Rita. So if you'd like to ask a question, or if you'd like to respond or give your own take on anything that Jim has said, or indeed on Peter's response to Jim's points.
Well, look, I didn't expect to be seen here. I'm still sort of lying in bed. There's quite a lot of skipping around and confusion. I'd like to go back to what James was saying about Planck's constant and the speed of light and the gravitational constant, like there was something arbitrary about it. And, oh my God, there's there could be hundreds, thousands of experiments saying something about that. There's nothing wrong with Planck's constant and those constants. So, like, I don't know where he's coming from about whatever his argument against it was. So now I did look at Peter's paper. Hey, Peter, it's nice to see you. I've seen your work before, way back. But anyway, it looks like what you're doing is that you're saying there is a hidden variable in some way of modeling a spherical particle to explain consistency with quantum mechanics and like why Bell's theorem is violated. And that's okay. I kind of like that. So keep up the good work. I do not understand it. I don't understand most of what you're saying and doing.
That's fine, Eric. You're quite a plain speaker, and that's appreciated. Now, could I suggest that maybe your detailed questions, which are very apposite, that you maybe hold those until Peter gives his presentation, maybe in 2 or 4 weeks' time. I think it might be 4 weeks' time, and we can address them in detail. Because what I'd like to do is I'd like rather maybe to get Jim's response, because he is the speaker today, and we'll deal with the clarifications of those very, very important points that you just raised with Peter when he talks to us. So is that all right, Eric? Yeah.
Right. Thanks for let me saying hello. Okay. All right.
Yeah. No. We wanted to say that because you've taken the trouble of coming into the green room. So thank you very much, and thank you for your points, which are always they're very concrete points about why we're questioning some things that have worked for a long, long time. You've raised those points before, and they are appreciated. So thank you again. And Jim, I think you're the next person. Harry is gone, but Jim is in the green room, and with your permission, you've no video at the moment, actually, Jim. But can you hear me? And Jim, I think you're the next person. Harry is gone, but Jim is in the green room, and with your permission, you've no video at the moment, actually, Jim. But can you hear me?
Yeah, I can hear you.
There seems to be a recording of my voice because it was repeated. But Jim, do you have any response? I know we've talked a lot about some other issues in fundamental physics, like MMX in outer space and Maxwell's equations and all that. But do you have any brief response, particularly to Jim's analysis of Peter's paper, or even to any of the clarifications that Peter has subsequently made?
Well, first
Good,
of all,
bad, or indifferent.
First of all, I'd like to say hello to Dr. Jackson. We've had a few brief exchanges on ResearchGate. I don't know.
Oh, excellent.
My advocacy of Ching Chuan Tzu's local ether model.
Yes.
I'd just like to address the issue of continuous versus discrete space and time. So you can have, in my opinion, you can have think of the ether is made of as electrons and protons made of smaller particles that, when they're free, are the ether, and those particles are made of the smaller particles, and so on and so on. So you can think of space as, in a way, continuous and in a way discrete.
Okay, that's an interesting way of looking at things. Not sort of a binary way, either or. So what I'm going to do is, I have Harry who's in and out. I'd like to get him up before we terminate today. But I'd like to ask Jim, who is our speaker, Jim Keene rather than Jim Morrison, to respond to Jim Morrison's points, and indeed any of the earlier points that were made, either by Eric or indeed Peter's response, although he may wish to leave that until the summary of his talk, which I'll give, as we're closing the meeting today. So I'll add you, James Keene, Jim Keene, and
Hello.
I'll give you a little response before we bring Harry in.
Well, first to what Eric Reiter said, I don't discard the fundamental constants as measurements. They are measurements as opposed to fundamental constants. If anything, they would be secondary constants derivable from more primary constants. But what I'm saying is that the values of Planck's constant, the gravitational constant, and the speed of light, which I showed in one slide, are measurements, and they are unexplained measurements. What the question I raised when I say unexplained is why aren't they 10x greater or 10x smaller than what we do measure them to be? So far, there's no explanation for that. Binary mechanics provides one, but other than that, I don't know of any other attempt to even explain why the measurements have the values that we obtain when we measure them. So that's my response there. Now, in terms of the reviewer identity, I might mention that most cases when reviewers are reviewing a paper or a grant proposal, they are anonymous. In other words, unusual today, we're reviewing someone who is, the reviewer is not anonymous. So I thank Dr. Jackson very much for being so kind in his response, and look forward to his more complete presentation in the future here in CNPS. But that's sort of a weird situation where the reviewer is not anonymous, although I tried to do the best I could. And plus, when we're reviewing each other's work, which is perhaps we might do more often here in CNPS, we have to respect the investigator. In this case, it's Dr. Jackson and his co-author, because these are individuals which are a rare breed. There are very few people on the face of the earth who sacrifice, and I'll use the word sacrifice, other pursuits such as, earning more money or more leisure activities in order to pursue science, to try to increase our knowledge of this universe and how it works. So there has to be a great deal of respect there. The other thing I'd like to know that would be great would be future research. For any paper or research proposal, I think the principal investigator should point us to how their work leads us to further experiments, either to support the veracity of their model or test it, or to go beyond it to what the next questions are. Whenever we answer some questions or propose some answers for some questions, as most of us try to do, there's always the next questions that if these answers are correct, then what are the next questions that need to be addressed? I hope Dr. Jackson can enlighten us on that ground. And I might mention, though, that the black boxes are still there in Jackson's comments, which I hope can be further clarified. For example, quote, the set of motions, quote unquote. Well, how do these motions occur? We talk about the sphere interacting with the next sphere. Well, how does that sphere move in the first place? Isn't that a fundamental physics question? So my whole theme, basically, to summarize and to close these comments, is are we pursuing physics and the big unanswered questions, like the measured speed of light is a basic mystery of physics. Why does it have that value and not some other value? I'll close with that. I think I've had my say already, so I'll let other people talk.
Right, and I may be bringing you back just at the very end, but Jim, Harry's computer has just given up the ghost, so he says. But here's his question: where in any physics textbook is it explicitly stated that space and time are continuous? Give me some examples where this is stated as an assumption. So that's Harry is questioning that.
Well, it's in the math. Just look at the math. Look at Newton's laws. The first law, the second law, the third law. They all assume that the space and time are somehow continuous. Otherwise, the vector additions that are involved there would make no sense whatsoever.
See, the differential calculus is based on discrete quantities, but in the limit, it becomes continuous because they vanish basically. They approach zero. So I suppose that's what you're saying. The calculus that Newton developed to explain his mechanics.
I think you're on the right track there. Yes.
Okay.
You see, in other words, like in terms of the three primary units of measurement, which everybody in physics uses, mass, length, and time, just look at the constants from the NIST.com. It's all, these three primary values. So the question is, can these be quantized or not?
And obviously you say the same about charge.
George who?
Charge. Say
Oh yeah. Charge. It appears, at least in my work, that we have fractional charge is 1/3 the elementary charge of the electron, and that's So that definitely is quantized. So in other words, the quantum physicists have gone on strike. They have declared the end of quantization with a charge, with things like the orbitals of electrons in atoms, the M, L, and N values, which are quantized. But beyond that, they pretty much gone on strike. There's no more quantization ever again allowed in mainstream quantum mechanics. They're all out on the picket line saying we will not quantize anymore, except for a small few that I did mention, like the loop gravity people, the loop gravity theory people, and mostly they're very obedient. They're using the magical mystery tour Planck limits, which I tried to show are simply more unexplained values. Since they're based upon unexplained measurements, well, you just get more unexplained stuff. It sort of would be nice if physicists said, well, why don't we try to explain some of this stuff?
The danger, perhaps, not among professional physicists, but among the public at large, is that quantum has sort of exercised the imagination. They might be aware of Planck's law and so on, nothing more, and it becomes a very attractive thing to say. They sort of generate a lot of kudos by saying, oh, this is all quantized and quantized, and it encourages them to believe in quantization of everything. So I'm just maybe cautioning how the public perception of this can be based on fashion rather than physics. But obviously that's another phenomenon altogether. So personally, I'm always very cautious about these things. And somebody here, I think it was in the comments, he said that maybe it isn't in either or, it's a bit of both. Now that may be a sort of a philosophical question, but
well, another duality. We love dualities, and
yes.
anytime, like in my first talk 2 weeks ago, somebody said, well, do I think the consequences of full quantization, which I presented 2 weeks ago, is actually a physical reality or sort of just a metaphor? Well, no, I mean, we're doing physics here. I'm not big in literature and poetry.
Okay.
But it astounds me how field theorists can believe that, if you want to be concrete, that there must be an infinite number of infinitely small supercomputers at every point in space to analyze this data and sum it all up to get what the field potential is at that point in space. That's miracles. That's religion. That's not science.
Right. Now, it's always very difficult to engage in a sort of a to and fro conversation on the nature of, say, continuity or otherwise. But Harry has come back. He says,
oh, good. I see the question.
Do you see it there? Yeah. The continuity assumption is in the real number system. Okay, so now tell us what mathematical system is going to replace the real number system.
Okay. There are three mathematical ideas which, when you reverse engineer the universe, can give you a fully functional universe. Just three. You don't need any more. One is a single digit binary number, 0 or 1. You have something or you don't. And by the way, these three mathematical ideas are already known to everybody who speaks a language because they're required to speak coherently. The second one is the AND function, where if you have one thing and another, then a third thing occurs. Or it could be a three input AND function, as in my definition of forces, where you have three things required, and when they're all true, then the force exists and a particle moves. The third mathematical idea is the not function, that if I have something and I apply the not function, then I don't have something. So with those three ideas, you can build a fully functional computer and a fully functional universe. Now, I would guess that most physicists today keep their software and hardware fairly much up to date and are fully digitalized in almost everything, except when it comes to theoretical physics. For everything in life, we'll go digital. But when it comes to our work in science, we'll stick with the old rickety analog computer ideas. That's my sort of...
Okay, that's the conservatism. But we're getting further on this, and I think we'll have to get Harry on to the green room maybe later, but maybe not today, obviously. But he says he raised this thing at the last meeting, actually. This pondering. I looked it up actually, but he's asking if you looked it up. Duality.
Well, it's another duality.
Yeah.
Are physicists going to spend all their time looking for more dualities? And where does that get you? What more do you understand about how the universe works? Tell me that. Frankly, I'm more interested in spending my time reverse engineering the universe than in looking at the flaws of the theory of continuous space and time, which leads to all of these dualities, paradoxes, contradictions, all of the adverse side effects of this theory that I mentioned. So it's just another adverse side effects. Yeah. Why would I even spend time looking at it?
Well, it could also be considered as analogous to the dialectic process, maybe an Hegelian type of process, where you look at the thesis and then you look at the antithesis, because there isn't 100% truth in anything really, but you look at the antithesis and then you got a synthesis, which is melding the two together and getting a purer truth. And then you engage in the process again. You get the new you get the new synthesis, and that becomes your thesis. But that isn't 100% true either, although it might be near the truth. So you get the antithesis, and then you meld them together.
I'm sympathetic to that kind of approach and analysis. And send me an email with the name there so I can look up this great duality. But this is just another adverse symptom of adverse consequences. What I tried to do is lay out what are the consequences of the theory of continuous space and time, and you have the dualities, the paradoxes and contradictions, et cetera, and what are the consequences of quantization of space, time, and energy, and pick up on Ian's last sentence. It's what flows from that. What are the fruits of that tree? What are the results? The future research, the future questions which can be asked. What advances do we make if we then can explain why the measurements of the speed of light and things like Planck's constant and electric charge are the values that they measure them to be, rather than being so happy with letting those remain as unknowns, unexplained measurements, and we're going to call them fundamental universal constants, and we're going to erect a temple and put a statue or sculpture of some sort for each one that we're going to worship. And we're going to ignore that we don't know what these things really are. I opt for doing physics instead of doing religion.
Yeah,
And, like if you want to do religion, that's fine. I've got no problem with that. But when we want to do physics, let's do physics and leave the religion out of it.
Right. Harry has come
Leave
back
the
again.
miracles
It's not
out.
for me to be a bit of an advocate in his absence, but he's saying that what we've discussed a moment ago is not an assumption of physics, it is an assumption of mathematics. He doesn't say it's an assumption of religion, but it's an assumption of physics.
Okay,
Sorry,
well,
it's an assumption of mathematics rather than physics.
I agree with Harry on that.
Right. Okay.
That's what I said. When the question came up, where is the assumption? I said, look at the mathematics. In all of the theories, in all the little piggies that I showed, look at the math. And what you're going to find is magic, miracles, things that theologians in the theology schools, departments at these universities would never accept as being just too outlandish. But physicists are very happy with them.
You're not getting away so lightly now. How does a particle move from one place to another in your physics? Your physics is just a mathematical substitution for physics of realism.
Well, perhaps one day I'll be asked to give a talk on binary mechanics, and we'll cover that ground.
You did give us maybe an introductory talk. It might be some years ago, and it might.
Yeah, it was a long time ago.
Yeah, exactly. It probably will be opportune to get you to give us an update on that. So we will hold you to that. No, more stuff here. There aren't actually many other questions coming in on the general comments. Just chat. So I'm not bringing them up. I'm concentrating on Harry. Harry says, we're running out of time now. All you are doing, Jim, is saying, I prefer a mathematics of Boolean algebra over the mathematics of the real number system. Any response?
I am saying that, yes.
Okay.
Because it works.
Yeah. Okay.
So why would you use more complex mathematics? He brings up a good point. Why would you use more complex mathematics when it's not required? There's a thing in science that we seek parsimony. Can anyone beat the parsimony that I've offered in those three mathematical ideas that I just enumerated? Nobody that I know of. If they are, step forward. Now, the more complex mathematics are used in engineering on macroscopic scale and are quite justified, yes. And a lot of the mathematics in quantum physics is stolen from statistics. I used to write statistic programs of principal axis factor analysis, which involves extracting from a correlation or covariance matrix the principal axis eigenvectors and eigenvalues. Well, this is what the quantum people are doing. Very complex mathematics. It's not just a simple quick walk in the park to write that software. You have to really know what the hell is going on in that math. And so a lot of what happens in quantum mechanics is that the physicists simply, redressed what they learned in statistics class, and dressed it up and walked it down the what do they call it, the walkway, in the physics show.
Right. So, and you were having recourse to Occam's razor there. I'll
Yes,
not,
sir.
Yeah, I'll not put this up, but I think Harry is taking a bit of umbrage at your use of language in regard to theologians. But for my part, I don't take any umbrage about it. I think it's
Well,
too
put
simple.
Harry up. Like
What?
we're all one happy family here, and we want to hear every point of view.
Well, okay. He thinks you're insulting theologians, but I don't think it's worth arguing about that. I didn't want to keep it silent. He
Well,
says
the theologians are a lot more reasonable. The miracles that they talk about are much more plausible than what the physicists put forth.
They frequently are. The only difficulty with a lot of theology, I suppose, and this is maybe a hard thing to say, but is it starts from the conclusion. It's a bit like Alice in Wonderland. It says sentence first and verdict afterwards. So that can be the case. But he says you reject the mathematics of Pontryagin. How do you know what you say is better? You don't. Ad hominem arguments are not acceptable. Okay, maybe it's being ad hominem. Maybe I've been ad hominem. We're all a bit ad hominem, I suppose. Okay.
Well, it's by your fruits you shall know them.
Yeah.
Okay, this is why I emphasize among the weaknesses that Jackson might consider, and he was so gracious. Again, thank you, Peter. Yeah. What is the future? What does this line of work, Jackson's model or my work or anybody's work, where does it lead to? What do you do next? Oftentimes in these sessions over the last year or so, I've raised that question, and usually I get a blank as if no one has even thought what next. Well, let's start thinking, with what you think is a good idea in terms of a physics model, what are the experiments that should be done to test your idea? I've done that with the case of, let's say, the lunar surface temperature affecting gravity. You can download data from the investigators and determine and do your own analysis. So here, which confirms my work. Well, let's do that. If you have a different idea, do some experiments, or what are the experiments that confirm your work?
Yes.
In some cases, like Eric Reiter, his work actually, in my opinion, confirms my work, and I applaud him. I want to write a paper on what he's done. He's done some great stuff.
Okay, well, that will be another subject that will be of interest. Actually, one thing we have found is that Harry himself gave 3 talks on the unipolar induction business and the induction more generally. So you might be asked to match him in that you'll be asked to give a 3rd talk in the not too distant future, updating us on your own work in binary mechanics, and that would be most interesting. But before I close the session, Is there anything you'd like to say further before, or anybody else wants to say anything else in the green room? Or would you like to say anything else, Jim, or have you?
Well, I'd just like to thank everybody. I joined this group of regular participants several years ago, I guess it's been now, and primarily to learn. And I've learned a lot from all of you, and it has helped me in my thinking as to how better present my own ideas. And I hope each of you has experienced the same thing, that this kind of interaction that we do here in these sessions can only help everybody say, well, I better address that, or I'd better take care of this point, and so forth, because I know it's something that people are going to come back for. That's why I created the side effects or adverse reactions slide to actually list the things that people raise about, well, what about this duality, or how about the newest paradox on the block this week, and so forth. Well, all of these things indicate weaknesses in current theory.
Okay, I'm just going to summarize, but I think Peter wants to come back. So if we can bring him back quickly, because we're running out of time. But yes, Peter, I have to unmute you. We can hear you now. Yes.
Yeah, a couple of answers to Jim's points, or a couple of hypotheses on Jim's points, is that in terms of, I see the wave particle duality and continuity problem as being merely a stage problem. You can always consider the next stage down, and in fact you can do it. It's exactly the same, exactly equivalent to higher orders in string theory. You consider that and Susskind's work, you get to ever finer dimensional changes, and it can be dealt with very simply in that way. So there's no point in having big arguments between the two, in that both can be incorporated in that theory. Now, also another interesting hypothesis, Jim, is that because electrons have such a high absorption coefficient, is that I've got a hypothesis that electron spin speed dictates C. It's electron absorption and re-emission that dictate local speed C in any inertial system, because electrons bound all inertial systems, refractive planes, astrophysical shocks in space. And so that needs some thinking about, because I've not found anyone able to disprove it, and all the evidence is to the contrary. But in fact, C is fixed by electron spin speed, effectively, on absorption and re-emission. Now,
I suspect you may not be a million miles away. But
well, I hope that Peter cannot be limited to this one paper, but in his presentation, just present his general thinking on many areas, such as what he just stated. And I really look forward to that.
Yeah, I'll have a dozen other papers.
Yeah, I know you do. Well, and I was even going to suggest another of your papers, Much Ado About Nothing, as something to look at. But what I hope is that you just present an overall view of physics according to Peter Jackson, if you will, rather than restrict yourself to this one measurement problem paper, because I think that would be very stimulating.
Yeah, on the fundamental thing about maths as well, I've got a very interesting one on FQXI, which was top scored in 2015. It's the red-green sock trick, which was fundamentally about quantum mechanics, but in fact it went right down to mathematics and saying, look, we've really got a lot wrong with Boolean mathematics, actually, so we can have a discussion about that, and integer mathematics, in that there is always a curve, a sine curve distribution, Bayesian, Gaussian, whatever you like. There is no 1 and 0. That is only a simplification for us, and that simplification is where all the problems arise. So yep, there are always smaller little wiggly bits on each up and down. But if you look up red-green sock trick on FQXI, yeah, I think you might find that interesting.
And my suggestion, basically, just to follow on our earlier points, is that you've been in correspondence with Dennis Allen, because he's been looking at your points and discussing with him. And if you maybe just feedback to him what has emerged today. I don't know if he's here. I don't see him in the questions. And maybe have a brief discussion with him about what Jim's point, that we'd like a panoply of your core ideas, maybe, rather than just one thing at your talk. And Dennis normally copies a few of us on those emails, so we can have a brief chat maybe over the next week as to what you might concentrate on, and that would be most appreciated, Peter, and we'll fix that. So it devolves upon me maybe to close the meeting, because we've just ran out of time this second. I think they'll give us a minute or two just to finish off. But I'd like to say, on behalf of the CNPS, and indeed all of you participating, because we have a large number on the social media participating. And sorry, Dennis actually is here, so fine. I'll talk to Dennis by email about this later. But I feel I'd like to thank all of us, all of you, on behalf of the CNPS, and indeed I feel very privileged to have been in this position today, where we had the benefit of Jim's further analysis, using his particular skills in regard to vetting projects and papers and so on. This, not an easy paper to comprehend, given by Peter Jackson. I've looked at, his bio and so on, and the privilege is that we actually have Peter in the background here, which he's been listening to it all, and he's come back. And I wouldn't have minded if he had been very critical of Jim, but actually he's been very complimentary, I think. So any words of mine would be really ocious, unnecessary. Peter has given the greatest gratitude that could be given to Jim for his analysis of this paper, and it's given us some hope for the future, that Peter will be able to expand from this particular paper on the measurement problem and exchanging momentum and all that, expanding maybe on a few of his ideas, which we'll be discussing over the coming week or so, with regard to feeding into our system, so that we can engage in further discussion about it. So I think it's been a very, very valuable talk today, and I'd like to thank Peter very much for having attended. But first and foremost, I should like to thank Jim for the considerable work that he's gone into this, his good nature in talking about things, little wit here and there, and his clear exposition. And I look forward. Keep an eye on the notices on the social media. The schedule is that there'll be a normal, I call it a normal talk next week, where I think again David de Hilser might be giving out a lifetime award, just as he did to Nick Percival some weeks ago. I think that may be on the cards. And then we would hope in 2 weeks' time to have a further talk, and maybe in 2 weeks' time after that. In other words, I think the 4th of March. Maybe if it's not too early, Peter might come back to us, but we'll talk about that. And we just have a very nice thank you, James, Peter, and Ian. Very, very kind from one of our Martusanes. He has talked to us before. He's been participating. So I'll wish you all a very good day. I think for most of you, it's only noon or something like that. For some of you, maybe it's early morning. For Peter and me, I think it's after 5 o'clock. So we have to prepare for the evening meal or something like that. So I wish you all a very good day, and thank you very much for participating. I'll end the broadcast now.